Today we will be exploring how momentum changes if the mass of the system changes. Primarily, we will be dealing with two extraterrestrial problems. First, we will deal with a rocket ship taking off into outer space. And secondly, we will deal with a meteorite falling back down to Earth. If we were to use the normal physics equations, it would not work because the mass of the system is changing. So we have to go a little bit deeper into physics.
Consider the spaceship the Enterprise, deep in outer space, far, far away from the surface of the Earth. As it maneuvers, its mass does not stay constant. The engine ejects fuel in order to create thrust to maneuver the spaceship. The burning fuel causes a collision in which the momentum of the system must stay constant. Therefore, the momentum of the ejected fuel must be equal to the opposite of the momentum of the spaceship. This can be represented in the equation change in momentum equals change in mass times velocity. If the change in mass is over time, the force exerted, also known as the thrust, is equal to change in momentum over change in time, or change in mass over change in time times velocity. Let's say our rocket ship ejects fuel at a rate of 13,800 kilograms per second and soars through space at a speed of 2,440 meters per second. This is just like the rocket in the example problem in our textbook on page 285. So in this example, the thrust by the engines of the spaceship will equal the delta m over the delta t times velocity, which will give us a thrust of 33,700,000 newtons. And so if this thrust is greater than the weight of the spaceship, it will force the spaceship in an upward acceleration. So at first, after takeoff, the acceleration will be gentle, but the acceleration will accelerate more abruptly as the mass of the spaceship decreases.
Now for the more perplexing problem of the meteorite. As the space rock enters Earth's gravitational field, it has a certain cosmic speed. That is the speed in which it travels through space. The air in our further reaches of our atmosphere, called the thermosphere, begins to slow down our meteorite. Eventually, it reaches a point called the retardation point, in which it has been slowed down enough by the air resistance that it begins to re-accelerate because of the gravity of our Earth. We are going to assume that it reaches this retardation point at Earth's mesosphere, which is approximately 140 kilometers above Earth's surface. It quickly reaches terminal velocity after reaching the retardation point, which is also about at the tip of Earth's mesosphere. For the sake of simplicity, we are going to assume and start our problem that at this point of terminal velocity. Furthermore, we're going to assume that our meteorite is a special silicate compound. Keep in mind that the mass of the space rock is changing, but we must assume that it remains a perfect sphere the entire time it is in descent. Therefore, based on the density of silicate, we can determine the volume of the space rock at its initial point. The volume of the space rock is equal to the initial 200 kilograms of the meteorite divided by 0.0041 grams per centimeters cubed, divided by 1,000 kilograms, divided by 1,000 centimeters cubed per meters cubed, which gives you 0.50 meters cubed. Next, we can determine the radius of the sphere, which is the cube root of volume times 3/4 divided by pi, which results in 0.492 meters. We then use the surface area of a sphere in free fall, which is equal to the radius squared times pi, which is 0.762 meters squared. Since we are assuming at the beginning of the problem that the meteorite is traveling at terminal velocity, we must find said terminal velocity. This is equal to the square root of 2 times the mass times gravity. all divided by the density of the substance in which it is traveling, air, divided by the drag constant, and divided by the surface area of the object in free fall. This gives us 92 meters per second, which is approximately 205 miles per hour. Since we know how fast it is traveling and how far it is traveling, we can find the time, which is 923 seconds. We can then find the force of the meteorite at its point of impact by calculating the change in mass over the change in time times the velocity, which results in 16.7 newtons. Likewise, the energy at the bottom of the descent is 1/2 of the velocity squared times the mass, which is equal to 135 kilojoules. The momentum at the end is equal to the change in mass times the velocity, which is equal to 15,456 kilograms meters per second.
When you compare these values to what they would be if the Earth had no protective atmosphere, the results are staggering. The velocity the meteorite would be traveling is approximately 2,894 miles per hour, which is about 2,689 miles per hour faster than the meteorite traveling through the atmosphere. Our meteorite traveling through Earth's atmosphere has about 0.0065% of the force and about 0.081% of the energy it would have if the Earth had no atmosphere. Wow. In both the case of the rocket ship taking off and the meteorite falling through the atmosphere, the changing mass of the object in motion calls for a whole new ball game.
Isn't physics great?